In section 4.2, we are going to review all of our postulates so that we can use these postulates and properties for algebraic proofs. So the first one is the reflexive property. Reflexive property means that a term is equal to itself. So an example, we have A equals A, 3 equals 3, 5 equals 5, anything where something equals itself. Symmetric property is where we have two terms and the two sides of an equation can be switched. So if we have A equals B, then we can also have B equals A. That's our symmetric property. Transitive property means that we skip the middle term in the conclusion. So if we have terms A, B, and C, if we know that A equals B and B equals C, then we can get rid of B in the middle and say that A equals C. Our addition property, we have an example, if A equals B, if we add C to both those sides, then they are still going to equal each other. So if A equals B, then A plus C and B plus C will still equal each other because we added the same thing to both sides. Subtraction property is similar. So if we start with A equals B and we subtract C from both sides, they are still going to equal each other. Okay, multiplication and division property, those are all again similar. So if we multiply both sides, A and B by C, they're still going to equal each other. And if we divide both sides by C, they are still going to equal each other. So all these properties right here, these are what we use to solve equations all the time. We use the addition, subtraction, multiplication, and division property by doing something to both sides of an equation. Then we have substitution property. For all numbers A and B, if A equals B, then A may be replaced by B in any equation or expression. So if we said that 2A plus 5 equals 10, and we know that A equals B, we could also write that as 2B plus 5 equals 10, and those would be the same thing. Our next one is the distributive property. So if we have A times B plus C, we distribute our A, multiply A times B, and A times C. Okay, then number 10, we combine like terms when variables are combined without moving anything across the equal sign. So if we had 2x plus 5x equals 20, we could say 7x equals 20. Combine our 2 and our 5. Okay, so all these properties should be pretty familiar. We've been using them a lot solving equations. So now we're going to use those to practice naming the properties that justify each statement. So in number 1 here, we have if 3x plus 7 equals 12, then 3x equals 5. So how did we get to that new equation? Well, if we subtract 7 from both sides, you have 3x plus 7 equals 12. Subtract 7, that's how we get 3x equals 5. So that is our subtraction property. Okay. Number 2, if AB equals CD, then AB plus EF equals CD plus EF. So we still have our AB and CD, but we're adding the same thing to both sides. So that is going to be our addition property. Then finally we have if PQ plus RS equals 18 and RS equals 18, then PQ plus 8 equals 18. So here we're taking our value for RS and plugging it in to our original equation. So that's where we get PQ plus 8 equals 18 from. So when we take that value and plug it in, that is called our substitution property. Okay, let's keep going. Okay, at the bottom here, we just have a couple definitions to clarify and help see what each piece of a proof is. So we have a postulate, which is what we've been using. Postulates are accepted to be true without proof. So another word for a postulate is axiom, but you'll probably see postulate more often. Then we have a theorem. A theorem has already been proven to be true, so we can use those theorems that have already been proven to justify other statements that are true. So we are going to use both postulates and theorems in our proofs, which is a logical argument, and each statement in a proof is supported by a reason. So in our proofs, we're going to have a line of some kind of information, and next to that line, we need to have a reason why that's true. So some of the reasons that you might use are different postulates, theorems, definitions, or properties. So this will make more sense as we get into some examples. Okay, so here we have an example of a paragraph proof. So our example is that we are given that M is the midpoint of PQ. So if we draw that, we have line or segment PQ, and they tell us M is our midpoint, so it's right in the middle. We want to prove that PM is congruent to MQ. So if we were to write that answer in a paragraph form, this is what it would look like. From the definition of midpoint of a segment, PM is equal to MQ. This means that they have the same measure. By definition of congruence, if two segments have the same measure, then they are congruent. Thus, PM is congruent to MQ. So you can do a proof in a paragraph like that, and another way we can write a proof is a two-column proof. This is what we are going to be using most often. So here we are given our information at the top, same as above. M is the midpoint of PQ, and prove PM is congruent to MQ. So when we do a two-column proof, we have our statements on the left side and our reasons on the right side. Our first statement is always going to be our given information. So we start with M is the midpoint of PQ. Got cut off there. And the reason for that is given. That's our easiest step in a two-column proof, to write our given information at the top. So then with that given information, if M is the midpoint, then we know that PM equals MQ. And that is our definition of midpoint. And if we know that PM is equal to MQ, those measures are the same, then we can say that they are congruent because that is our definition of congruence. So that is what we'll be using for our two-column proofs. So if we look below at our next example, it says to solve for x and show every step. So if we start with this equation here, this is our given information. Our first step to solve for x is to subtract 18 from both sides. When we do that, we have 2x and negative 12. So this, the reason we can do this is our subtraction. Okay, and if we use our subtraction property there, the next step to get rid of that 2 is divide both sides by 2. And we get x equals negative 6. And this was using our division property. And when we get to the point, the end point, that is our answer. the bottom of our proof. Okay, so let's look at another example. This example says write a complete proof for the situation. Prove that if AB equals CD, so this is our given information, the top. If AB equals CD, AB equals 4x plus 8 and CD equals x plus 2, then x equals negative 2. So we need to set up our two columns. We have our statements on this side and our reasons on the right side. So our first statement is going to be our given information. We are given that AB is equal to CD. And the reason we can write that is that it is given. Then our other given information is AB equals 4x plus 8 and CD equals x plus 2. So we need to write that in our statement. We know that AB equals 4x plus 8 and CD equals x plus 2. And again, the reason we can write that is it is given. Okay, the next step is I'm going to take that AB and that CD and plug it in and set them equal to each other. So if we say 4x plus 8 equals x plus 2. When I substitute those in, I'm using my substitution property. So now I'm going to solve. If I bring my x terms over to the left, I'm going to subtract x from both sides. When I do that, I get 3x plus 8 equals 2. So now I got to put the reason why I subtracted x from both sides, and I can put my subtraction property because I'm subtracting the same thing from both sides. My next step is I'm going to bring my 8 over with the 2. So if I subtract 8 from both sides, I get 3x equals negative 6. And again, my reason is that I'm using my subtraction property. And then finally, I'm going to divide both sides by 3. And when I do that, I get x equals negative 2. And I use my division property to divide both sides by the same thing. So now my statement is what I was looking to prove. So that is always going to match your last line in your proof. Once you get to that statement, you know you are done. Okay, one more proof. Write a complete proof for the situation below. Prove that if this is true, then this is true. So our given information is going to be this equation at the top. V equals 1/3, pi r squared h. We are trying to prove that h equals 3v over pi r squared. So I'm going to set up my two columns. My statements and my reasons. My first statement is always the given information. So all I need to do is copy that down. I have v equals 1/3 pi r squared h. My reason is it is given. Okay, so I'm trying to get h by itself. So I need to get everything else away from h. So if I have my 1/3, I want to move that fraction over to the other side. I can multiply by 3. Or if I want to get rid of all this stuff right here at once, all this stuff right here is being multiplied by h. So if I want to get rid of all that stuff being multiplied by h, I can divide by all that stuff being multiplied. So I have v divided by 1/3 pi r squared equals h. And when I have a fraction like that, it is equal to 3v pi r squared. So right here, this is saying 1 over 1/3 is equal to 3. That's where I get that 3 on top from, right here. So the reason I can divide all that stuff is because of my division property. Now you could do it one step at a time. You could say, first I'm going to multiply by 1/3, multiply by 3 on both sides and use my multiplication property. And then I'm going to divide by pi and use my division property. And then I'm going to divide by r squared and use the division property. And you still end up with the same thing. Or you can do them all at one time and end up with the division property. And so this right here, we're already at my final proof. So this proof might only have 2 steps, depending on how many steps you did it in.